Welcome back to the deep dive. Today we are pulling back the curtain on something that's absolutely critical to our digital world, but not always well understood: the API. I mean, this is the architecture that lets everything from your banking app to your smart thermostat talk to a server that could be anywhere on the planet. So we've taken a stack of sources, all compiled under the title Mastering APIs: Architecture, Security, and Management. And our mission for you is simple. We want to give you the shortcut. We want just move you from just knowing what an API is to really understanding how they're built, how they're secured, and how they're operated in the real world. So let's start with the absolute fundamentals. An API. At its simplest, it's just a way for systems to communicate. A contract.
Exactly, a contract. And that definition, as simple as it sounds, it immediately forces you to start categorizing things. Because those rules of interaction, they change completely depending on who's allowed to use the API. So you have to establish some structure right away. And the sources break it down mainly by audience. So first you have public APIs. These are open access. Think of how Yelp or Google Maps lets any developer just build on top of their data.
Right. Anyone can sign up for a key and start building.
Then you have private APIs. These are the total opposite. They are strictly internal. They let service A talk to service B inside the same company. They never, ever see the public internet.
Okay, so public and private, I think most people can kind of wrap their head around those, but there are a couple of others that get a little blurry.
Right. So next up are partner APIs. These aren't public, but they are external. They're for trusted business collaborators. Think of, say, a bank sharing specific data, but only with a verified financial partner who has a contract.
So it's a lockdown external connection.
Precisely. And finally, you have composite APIs, which are really a strategic tool. They basically take a bunch of complicated calls to maybe 3 or 4 different services, and they package them into one single clean request.
So if I'm a mobile developer and I need to get, say, 5 pieces of information from 5 different systems.
You just hit that composite API one time.
And it does all the messy work in the background. That's a huge efficiency gain.
It is. So knowing those 4, public, private, partner, and composite, that really frames the whole conversation, because every other decision flows from which type you're building.
Okay, so with that foundation, let's unpack the architectural styles. This is where we get past the what and into the how, how the data is actually structured and moved around.
Correct. And we really have to group these by what they're used for. For modern web services, the stuff that runs most of the internet you use every day, you're looking at 2 main styles: REST and GraphQL.
REST is the big one, right? The veteran is what most people learn first. You use standard HTTP verbs.
Yep. Get, post, put, delete. And you treat data as these resources you access with the URL.
It's simple, it's stateless, it works.
It does. But the big shift recently has been towards GraphQL. With REST, you kind of have to take whatever data the server decides to give you in its standard package.
You get the whole user profile even if you only wanted the name.
Exactly. GraphQL flips that on its head. It lets the client say, your phone, tell the server exactly which data fields it needs. Nothing more, nothing less.
And that is the huge aha moment for efficiency, isn't it? If I just need a user's name and email, why should I download their entire 100-field profile?
The impact is massive, especially for mobile devices on slow networks or when you're paying for cloud bandwidth. It solves that overfetching problem, which saves money, and more importantly, it reduces latency. The app just feels faster.
Okay, so that covers the modern styles, but a huge part of the enterprise world still runs on something much older. It runs on SAP.
The legacy workhorse. It stands for Simple Object Access Protocol, but simple is a bit of a misnomer.
I've heard that.
It's much stricter. It usually uses this very verbose XML, and it requires this document called a WSDL to define the contract in painstaking detail.
So why do huge banks and old enterprise systems still use something so, complex when REST is right there?
Rigor. That's the one-word answer. SO has strong built-in features that REST just doesn't have out of the box. Things like guaranteed message delivery, built-in security standards, and critically transaction support.
So when failure is absolutely not an option.
Exactly. When you need a rock-solid audit trail and guaranteed sequencing of events, SOP provides that enterprise-grade reliability.
So REST and GraphQL for speed and flexibility, SOP for strict auditable rigor.
Got it. But what about all the services talking to each other inside a big system, like in a microservices architecture? That is the perfect place for our 4th style, gRPC. The sources are really clear on this. gRPC is for fast service-to-service calls. It's all about cutting down overhead. It uses something called protocol buffers to serialize data, which is way more efficient than text like JSON, and it runs over HTTP2. That means you get persistent connections and can send multiple requests at once. The result is just dramatically lower latency. It's the speed demon for internal traffic.
Fantastic. So those four cover the standard request response model, but a lot of communication isn't like that. Sometimes you need a constant stream of data or just a little tap on the shoulder saying, hey, I'm done.
And that's when we have to pivot to what we call event-driven patterns. If you need a persistent two-way connection, like for a livestock ticker or a chat app.
We use WebSockets.
Exactly. It's a dedicated open channel for ongoing data streaming.
But what if I don't need a whole stream? What if one system just needs to tell another, hey, that order was processed, and that's it. No reply needed.
That is the perfect use case for webhooks. They're basically just callbacks. System A gives System B a URL, and when the event happens, System B just sends a simple POST request back to that URL. It's a notification, not a conversation.
It inverts the whole communication pattern.
It does. And for really serious, high-volume asynchronous messaging, you need dedicated protocols. The two main ones are AMQP and MQTT. AMQP is the heavyweight. It's for complex business logic where you absolutely need guaranteed delivery. MQTT, on the other hand, is super lightweight.
And that's used for
IoT, the Internet of Things, devices with minimal power and bandwidth. MQTT is designed for that environment.
We've covered a huge architectural landscape.
Yeah.
And that leads us directly to the next critical layer because none of this matters if it's not secure.
Security is not an add-on. It has to be the foundation. And it always starts with two concepts, authentication and authorization.
Okay, define the difference for us because this is where people get tripped up all the time.
Authentication is simple. It's proving who you are. Are you really Bob? Authorization is what happens next. Now that we know you're Bob, what are you allowed to do? Can Bob read the data? Can he delete it?
Right. Who you are versus what you can do.
For authentication, the industry standards are things like OAuth or JWTs-JSON Web Tokens. Oath is for delegated access. You know when you sign into a new app using your Google account?
Sure.
That's OAuth. You're giving that app permission without actually giving it your Google password. JWTs are a bit different. They're self-contained tokens that have proof of your identity and permissions baked right in.
So the API can just look at the token and doesn't have to call back to some central server every single time?
Exactly. It's way more efficient, which again is a huge driver in these architectural choices.
But security is more than just identity, right?
Oh, absolutely. You have to protect the service itself. That's where things like rate limiting come in.
And that's not just to stop hackers, is it? It can be a business decision, too.
It's often a cost control measure. If one client is hammering your database 10,000 times a second, your cloud bill is going to explode. So you cap them at a reasonable level. And of course, the absolute non-negotiable is that all data in transit must be encrypted using TLS.
Transport layer security?
Without it, your passwords, your data, everything is just flying across the internet in plain text. It's unthinkable today.
So once we've locked it all down, we can move on to design. Because a secure API is great, but if developers can't figure out how to use it, it's useless. Good design starts with really basic things like following RESTful conventions, using logical noun-based URLs. And you have to have clear versioning.
Oh, versioning is critical, usually putting it in the URL like V1 users, because when you have to make a breaking change for V2, you can't just shut down everyone who is using V1.
And what about when a request could return a million results?
Pagination. You have to support pagination. It's a simple idea.
Right.
You force the client to ask for data in manageable chunks. Give me the first 50 records, now give me the next 50. It prevents server overload.
All these best practices, they lead to this sort of gold standard of design that I've heard about but always found confusing, HADIOS.
Ah, yes, HADIOS. The acronym is a mouthful. Hypermedia as the engine of application state.
Right.
The aha moment is realizing it turns your API from a static instruction manual into a self-guiding website.
Okay, unpack that for me.
Well, when you browse a website, you don't look up what the next link should be in a book, do you? The website itself presents you with the links you can click next. HADIOS does that for APIs.
So the API response doesn't just give me data.
It gives you data and it gives you links, hypermedia controls that tell you what valid actions you can take next.
So if I request an invoice that's pending, the response might literally include a link that says action. approve payment.
Precisely. And another that says action, contact accounting. The consuming system never has to hardcode those URLs. It just follows the links the API gives it. It makes the whole system so much more resilient to change.
That dynamic nature makes it even more important that the initial entry point is well documented. So let's talk about the operational toolkit, starting with that documentation. You said it in the sources. Clear documentation is how developers succeed quickly. If they can't figure out the inputs, the outputs, the error codes, they're just going to give up.
They will. And this is where standardization is a lifesaver. Swagger, or as it's now known, the Open API specification, is the foundation. It's a standard way to write a machine-readable contract for your API.
And once you have that contract,
you unlock this whole ecosystem of tools. You can automatically generate documentation, client code, even the first draft, your tests.
you also see tools like Postman collections mentioned everywhere.
Yes. Postman is essential for packaging up example requests so developers can easily try things out, and for turning that dry OpenAPI file into something a human can actually read and navigate, you use tools like Redoc.
Okay, so we've documented it. Now we have to prove it actually works. Let's talk testing.
Testing is all about validation. You have to validate functionality. Does it do what it says? Performance, can it handle the load? And automation, can we run these checks automatically every single time we change the code?
So what are the key tools there?
The sources list a pretty standard toolkit. Postman is a go-to for functional testing of REST and GraphQL APIs. For those older SOAP services we talked about, SoapUI is still the king.
And for performance?
When you need to really stress the system, you turn to something like JMeter. And to tie it all together in your deployment pipeline, you use a command line tool like Newman to automate running all those Postman tests.
Which brings us to the final layer.
Yeah.
Management. You've built it, you've tested it. How do you actually manage millions of requests hitting this thing every day in production? This is where the API gateway comes in. It's like the single front door for all your traffic. It sits in front of all your backend services.
And it acts as the enforcer. It's the component that actually checks the OAuth token. It's the one that applies the rate-limiting rules. Without a gateway, every single one of your services would have to build that logic itself, which would be a nightmare.
And management is more than just being a traffic cop, right? It's about the long game.
Absolutely. It involves lifecycle management, how you roll out new versions, how you gracefully retire old ones. And critically, it's about analytics. You have to be monitoring usage, error rates, performance, and latency constantly to make sure the system is healthy.
Okay, let's bring this all together. We have the architecture, security, design, and management all mapped out. Now, finally, you have to actually write the code. You have to choose a development stack. And the framework choice often comes down to what language you're comfortable with. If you're in Python, maybe you're looking at Django REST or the much faster FastAPI. In the Node.js world, Express is still dominant.
And in the big corporate Java world, Spring Boot is really the established standard for building these robust enterprise-grade APIs. But here's the final, and I think most critical point for you to take away. The framework you choose. That's just one piece. Regardless of which one you pick, that code has to plug back into everything else we've talked about.
It has to connect back.
It has to. Your Spring Boot application must be able to generate that open API documentation. Your FastAPI code has to support JWT security. It has to respond correctly when JMeter is throwing thousands of requests at it. The architecture and the operation are two sides of the same coin.
What an incredible tour. We started with the basic API types. We navigated the trade-offs between, say, the efficiency of GraphQL and the rigor of SOP, the sheer speed of gRPC. We grounded it all in security with OAuth and TLS. And we saw how a concept like HADIAS can make an API almost guide you by the hand.
If you walk away with one strategic thought, it should be this. Mastering APIs is all about managing tension. You are constantly balancing the architectural need for speed using things like gRPC or MQTT against the operational need for rigid, uncompromising rules.
Read versus control.
Exactly. Every decision, from rate limiting to strict versioning, adds a little bit of friction, but that friction is what buys you reliability and security when you're operating at scale. The real art, the real challenge, is designing systems that are fast enough to compete, but also strict enough to survive. That tension, that's the daily reality of running a successful API program.
A perfect thought to end on. You now have the map, the vocabulary, and the strategy to really start mastering this world. We'll catch you on the next one.